Thanks a lot for the very nice introduction. Thanks also for the invitation. I'm excited to be back in Australia after many years, and then particularly through this honor provided with the Treasurer Fellowship. I am excited to share with you this evening basically my passion and why we do what we do. And you will see that actually I have not much new to say, that one of our specialties is indeed rediscovering or bringing back principles from the past, from past master builders that perhaps we should reconsider and bring back. So let's maybe get going. I like to start here. Because you're not from Zurich, I might need to explain a little bit what you're looking at. On the top, you see the construction of the dome of ETH Zurich in concrete, and on the bottom, the construction of the only high-rise in Zurich, the Prime Tower. And being slightly cheeky, one could argue that the only thing that has changed in this almost 100 years is that people are wearing helmets. So this is maybe a good starting point, because clearly the world around us is rapidly evolving. So why does our industry still design for constructions that are being built like this? I want to start there because this is an issue. It's an issue because we have estimations that in the next 30 years there will be at least 2.1 billion more people on this planet. And the way we are constructing in our outdated ways has a lot of impact indeed on our planet. So what does this mean, providing infrastructure, dwelling, housing for these 2.1 billion more people that need to be on this same planet? Bill and Melinda Gates in their 2019 annual letter calculated this for us. It's basically building the equivalent of one New York City every month for the next 40 years. So just to give you a little bit of a picture of how much construction needs to happen in order to provide for all of these people. Again, this is a challenge because already nowadays we are, as an industry, extremely polluting. So that is a first challenge. Particularly, I will focus on carbon emissions. And it is incredible to me that this seems to not be common knowledge, that people seem to suggest that we need to go to work using a bike or public transport, that we should fly less, but in fact we are challenging, we're almost as polluting as the transport industry altogether. On top of that, we are very irresponsibly indeed using natural resources, and the way we construct, we are depleting those. As an example, 80% of the world's urbanization of new building goes up in concrete. And one of the three ingredients of our favorite material to rapidly grow, sand, is estimated to no longer be available in the next 35 to 40 years, at least not in economically feasible ways. And then to make this picture even more rosy, we are also a major waste producer, and particularly landfill waste. So even though there is a lot of increasing efforts in recycling and so on, this is a global number. We are already, so this is actually wrong. It is not to estimate it in 2050. This is already currently going on. And if you look at certain areas, like for example Baden-Württemberg in Germany, the number of waste produced by our industry is 54%. So this is a gigantic impact. So I hope that with these few statements that I hope that all of you actually are very aware of, I expect that you might agree that we need to design and change the way we design and build our structures indeed. We need many solutions, we need many strategies, we need a change yesterday. But what I will show is in our work, we introduce something that we indeed call strength through geometry and material effectiveness, and I will explain what both terms mean, in order to provide really disruptive solutions. And we do this through state-of-the-art now developments and opportunities in computational design and digital fabrication. The reason I care about this as hybrid architect engineer, as structural designer, as I would call me, is because this is a very typical or an average picture which you see when you want to build a bit higher. So this is the typical weight distribution in a building for at least 10 stories and up. So this, what we're looking at is that 3/4 of the weight of the building is actually in its structure. And so this is an absolutely ridiculous situation, or you could even call it a chicken or the egg issue, because this actually means that the structure is actually there to keep itself up. So by the way, when you look at the imposed loads, there a very small fraction is us, the users. So just to put that in context. So I hope with this initial statement, it's clear that as structural designer, you can significantly influence that. And indeed, these will be 3 strategies that I will talk about to first reduce the structural volume by actually having better structural geometry. Resource depletion I will address through funicular form. That means compression-only form, like vaulted geometries, like Gothic cathedrals and so on. And what is special there is that reducing the structural volume in any prediction, any scenario of global warming, that just will not do. A little bit less bad is not enough. And so what we can achieve with actually activating compression in these vaulted geometries is that we can not only reduce the structural section significantly, but for these very thin sections, we can actually use very low quality materials. And this is an important opportunity because the pollution of a material goes almost one-to-one in hand with how strong that material needs to be. And then last, this will be an important aspect of what I want to share today, is that structural geometry is non-standard geometry. And if we don't find waste-free, efficient, economically viable strategies to realize these non-standard geometries, then anything I have to tell you is just an academic discourse and will really absolutely never have an impact. All right, so let's go through these different concepts that I introduced earlier. First, strength through geometry. I did my PhD at MIT, and in fact, indeed, in a very different field, as was introduced earlier. I developed a new method to understand and evaluate the stability and the safety of historic structures in unreinforced masonry. I like to start with these beautiful shells at Cambridge University. This is at King's College. This is a chapel of King's College. You might not know that if you look at these shapes, they span 13 meters, so 13 meters, with a structural shell, unreinforced stone shell, large pieces of stone that is only 10 centimeters. And if you calculate the ratio of the thickness over the span, if you were to cut an eggshell in half, that is literally the thickness of these structures. So, starting my research and looking at these structures, I realized that they're extremely poorly understood, but also that modern designers and engineers would not dare to sign off on a structure like this. And it made me appreciate that perhaps there is something that we have lost in design and engineering indeed. We developed computational tools to actually rediscover these forms, tools that are white box, so that actually expose the relation between form and force and to the designer. But you can do anything you want in computational simulation. And that is why we took indeed the 2016 Venice Biennale as an opportunity to make a statement. At that Biennale, we decided to make a 16-meter span unreinforced cut stone shell. So what you're looking at are 399 cut pieces of stone that are held together just by geometry. So what you're looking at is in equilibrium, without even mortar, without glue, without reinforcement. And so we did this extremely absurd, because it is so different than anything else that we do nowadays, kind of statement, to really make sure that our colleagues understood and were shaken up and understood that perhaps there is other ways to design. So here just also showing this thin sheet of stone that is kept in equilibrium. In this case, we are 1/3 of the thickness of an eggshell compared to the span proportionally. Of course, these kind of projects, they cannot come together without designing for those. So we developed this entire pipeline to go all the way from a constrained form finding a problem all the way to construction. By the way, for this we had only 5 months. 5 months for design, engineering, convincing the Italians that we were not absolutely crazy, fabrication and construction. I must admit that the third step was extremely challenging and they made us work for this process. This actually was how we started, and this is also how we approached the project. But to be honest, as much as I will advocate that these kind of problems or these kind of design challenges cannot be achieved without computation in every step from design, engineering, logistics, all the way to efficient fabrication, I also am a very strong believer that you need to think first, because if you put crap in the computer, then crap might indeed come out. And so these are the real sketches that we did in the beginning. These are my own sketches to try to understand the relation between the boundary conditions on the site and the geometries. And then we continue digitally. So this is actually digital sketching. Because as I mentioned, these tools, which we share for free, this is RhinoVolt, and RhinoVolt 2 is coming out in less than a month, so an upgraded version for all the RhinoVolt fans. No worries, it's coming. And so this allows you really to very explicitly start to sculpt and shape these kind of beautiful equilibrium forms. This was an interesting moment when we were ready to start fabrication. Our contractor, our stone experts, the Escobedo Group in Austin, Texas, did a calculation, and this would have taken 2.5 years, not 1 month. And so then we realized that indeed we should take advantage of these more advanced cutting techniques, like for example these diamond encrusted wire saws. So it's basically a hot wire cutter for adults, and these multi-axis kind of blade cutters indeed. So how did we achieve to go from 2.5 years to 1 month in fabrication? Here an overview of the steps. So a key thing is when you do 3D milling, complex kind of operations, never have to change or move the blank. Saves a lot of time. That is what you see on the left. Then we use these very efficient blades that really cut through this limestone like butter to make the interfaces. And the doubly curved inside was approximated just with a few kind of rough cuts that were then hammered away by Hector. So one guy was in charge to hammer away all these little fins so that they would look a little bit similar. We did have to also custom design some profiling tools, and this opportunity we took to then include these little 6 millimeters reference elements. The reason that we needed these profiling tools is because every stone had to be within 0.4 millimeters in global tolerances. Otherwise, this 3D puzzle would really not come together. But this actually helped us in engineering as well. So this was mainly a reference. Imagine that we are talking just about 5 centimeters. And so the masons had to place the stones exactly where they needed to be. We didn't have the references anymore. As you see, we had this rough cut for fabrication optimization on the inside. But as I mentioned, for engineering, this was a key breakthrough moment. Because one thing that we try to also clarify in this process is that you could make a model of this complex geometry, and you could think that this is a perfect world situation. In reality, all these stones will have tolerances, not everything will touch perfectly. So what this mini reference mark gave us is actually, as a structural engineer, we could have the guarantee that stones would not have local sliding. And so that allowed us to really simplify the engineering approach and to focus on very intuitive methods indeed. So here are some images of this stone vault being brought together. And maybe another thing to highlight is that we wanted to make this piece very educational, and all the cuts on the inside are actually aligned with the global force flow to make the visitor actually understand how this structure works indeed. You also see that it has this unique aesthetic that we of course celebrated, but the aesthetic is entirely driven by these fabrication measures, these optimization methods that we introduced earlier. So this structure stood very happily for 5.5 months during the Venice Biennale, and is now unfortunately in boxes waiting for its final location, probably somewhere in Austin, Texas. Obviously, we don't do these kind of crazy things without a lot of prototyping. This was one of our very early prototypes, models that we did in 2010. As you can see, this was quite an exciting day. We don't get to destroy our own structures typically. A bit of making fun of my PhD students that clearly are not used to handle a hammer is appropriate, I think, but anyway. So something that you see is the robustness, the resilience of these doubly curved geometries, that even if you take the supports away, they still stand. And so this is maybe an important message that indeed geometry is a key factor in the stability of systems, even entirely unreinforced. I will now shift gears to quickly show a project that we had nothing to do with. This is a project by Sami Padora in India, where they developed this exciting roof for a library of a local school with an extremely tight budget. But then suddenly I started to learn about this project, and in fact, in a very interesting way. Suddenly, we got full credit for the design of this project because Samip and his team kind of argued in the description of the project that the design was thanks to and entirely because of RhinoVault. And I just wanted to show this as a quick anecdote because many people have questioned us why we share everything we do, why we open source share all our methods, why we develop tools for others to discover structural form and so on. And I think this is actually a nice message that 8 years after we did this sharing, that actually we got credit for the design of probably the most beautiful project that was ever done with RhinoVault. There's many beautiful anecdotes about this project indeed. This seems very extensive and crazy, but what you're looking at is actually the reinforcement of a building to be built next to the site. And this is just some bent reinforcement in transit, and it was used temporarily to describe the geometries that allowed then local masons that had never done tile vaulting to basically realize these exceptional shell in a very beautiful way indeed. Here are some details. I just proudly show it because I think it's a nice message that sharing actually might end up being quite exciting later on. And indeed, how exciting is it to build a project in a context where you don't have to bother about handrails and things like that. So these are the teachers, in fact, running over the roof. All right, so strength through geometry was the first message. And there I wanted to say that you can do exceptional things with humble materials, unreinforced, by actually getting the geometry right indeed. What about this material effectiveness? So maybe it sounds peculiar. I'm not talking about material efficiency. And so I want to, through some examples, kind of clarify what that means. I'm talking about using a material in the way that it wants to be used and not necessarily the drive and the kind of the search for lighter and lighter. So basically a light structure could be more polluting than a heavy structure if you use, again, high polluting, high-tech kind of materials. Also there, I will look to the past to kind of discover and show some examples how this works. So here, for example, maybe you recognize these beautiful vaults, tile vaults in the Oyster Bar. This is in Grand Central Terminal in New York City. And they were built with a traditional Mediterranean technique that allows to build these shells without any centering. So here you see these tiles being placed. So you have some boundary conditions, and then with a fast-setting mortar you can build this. I'm going back all the way to 2008, or this construction was in 2007, of a project that I was lucky to do the engineering during my PhD, a project by Peter Rich Architects and John Oxendorf. It's the Mapungubwe Interpretive Center in the middle of nowhere at the border with Zimbabwe in South Africa. There we translated this traditional technique where you first build these boundary conditions on formwork, and then the white mortar is this fast-setting mortar that allows to build without any support. So all the timber that you see is actually guide work to guide the unskilled laborers. These were a week earlier still farmers and carpenters that were introduced into this new technique. These kind of transfer projects are extremely exciting because you also see the excitement of the local laborers that are doing these unique kind of new techniques by themselves, and the project nicely blend in with main spans of 18 meters. But why I'm showing this project is because really everything was done with local resources, both local labor and local materials. So what you're looking at here on the top left is actually and this depends on the type of soil, but the soil locally on site needed only 7% of cement, and then it could be manually pressed without firing the bricks, so just letting them dry and cure. And this then created these tiles that were used for construction. So in the middle, 12 people were employed for 1 year, which was important in the brief. It had to be a poverty relief program, and these tiles were then indeed prepared. But why am I talking about this project? Because this was actually one of the most eye-opening moments in my career, and I want to contrast these two images. You see these happy ladies working on the right, and you see that they're bringing these tiles on site in little packages of 3 or 4. This is because this is a picture of week 2. What am I talking about? The tiles are designed to only take 2 megapascals in compression, so that is basically peanuts in compression, 10 to 15 times less than a regular standard concrete used every single day. But if you take one of those tiles that are about 25 centimeters, you can just break them in your hands. So they're not designed to take any bending. And first week indeed was an entire disaster because the men couldn't be bothered, and more than half of the tiles arrived broken on site. And so this, why I tell you this anecdote that I learned from the Kiwi master builder, in fact, James Bellamy, is that these weak materials, if you place them where the forces want to go in compression, this becomes a safe structural geometry that is still standing there after many years now in active operation. It is a museum for African art. All right, so how does that work? If you don't activate double curvature or good geometry like what we did in the Armadillo Vault, an arch is very good and very efficient to take a certain loading case, for example, the self-weight. But if you have a large point load, like people standing on one side of the vault, the red line represents the resultant of the compressive forces in your system, and if they exit the section, this basically would mean that that arch would collapse. So another strategy than activating double curvature is actually to locally stiffen those arches by increasing the structural depth, by providing load paths for these compressive lines. And then if you add a tension tie, then rather than thrusting on the neighbors, you actually resolve the forces that you can, so that you can basically place it simply on a wall. And indeed, placing simply on a wall, what we have just done in these 10 seconds together, we have developed together a 70% lighter equivalent of a floor plate. So basically, by reintroducing these principles in historic houses, you see these arched basements everywhere. Just by reintroducing that, you save more than 70% of material. So this is something that really clicked with me, and where I understood that it's not just about activating weak materials, but these are really disruptive benefits that make sense in many contexts indeed. So these are these beautiful tile vaulted floors. You see also the tension ties. It's not just the curved geometry. You need to resolve the forces. And this is, of course, very different than what we see in the current practice of low-cost housing. This is, for example, an image I took in Addis Ababa, where there is nothing low-cost about this, and where also very bad scaffolding systems are used. If you go to the Venice Biennale, this is a project that we did for Norman Foster, and so you can still see it at the end of the Arsenale. This was a follow-up project that we did in the context of his drone port in Rwanda. Maybe another image, just to kind of, another project to kind of go on this idea of even recycled, very bad materials could become structural. So inspired by our little buddy Wall-E that indeed compacted waste to start building his cathedrals and skyscrapers of waste, we found, my colleague Dirk Hebel found indeed a beautifully recycled material, here Tetra Pak. But this material has absolutely no structural properties. 1/10 of the compressive strength of timber, which is not that spectacular, that's still okay. But 1/100 of its elasticity modulus, so it's basically a very flimsical material that is not meant to be structural indeed. That sounded like music in my ears, a perfect material to demonstrate again that actually if you get the geometry right, that you can provide a very safe structure. So this is the process of this material that is a kind of a replacement material for sheet rock, no, something. And here also we use the logics of unreinforced masonry to be able to assemble this very simply without needing any glue, any nails, any connectors except for these plastic wrapping sheets, and we could do this with the cheapest labor available, which obviously are students. Why it was important to keep it unreinforced is because an important part of the message was actually to recycle these elements again and put them back, so back into the recycling loop, into the circular kind of logic of these materials. Obviously you see that this arch appeared, but we had a little bit of fun here. The orange are orange juice, the blue are milk cartons, and then we had wine cartons on the other side. And so this structure happily stood for only 3 days. That's why we didn't want to leave any waste behind. And indeed, every single piece got re-shredded and put back into the factory. And so for 3 days, we generated this little cathedral of waste in New York City. I was getting a bit annoyed that everyone called me the arch guy. So I decided to show that structural geometry can also work in different shapes. And we did this with an even more stupid material, mycelium. So I talked about 2 megapascals in compression. This material takes 0.2 megapascals in compression, so 10 times less than peanuts. And there we showed a fully 3D structure, a branching structure that stood in an exhibition for 1 year in South Korea. And we're talking about 4 by 4 by 3.5 meters. So this is actually a quite sizable piece that has full load-bearing mycelium indeed. All right, but computational design is important because we need to actually bring all of these constraints together, and we want to actually demonstrate that if you rethink structures or design in such a way that you can achieve these efficiencies indeed. So, but let's remind ourselves again of what good structural form can do. This is a Pringle carrying its self-weight in 500 times its self-weight in quite a bad loading case. Do try this at home. This is quite spectacular. But what I didn't show you very clearly is that the Armadillo Vault was built on this extremely extensive, expensive, and wasteful formwork. So can we actually develop systems that we can start to assemble these kind of shapes without the need of any formworks indeed? So here we developed this kind of new voussoir stereotomy that have these interlocking parts that work with stable sections that basically allow anyone in no time to assemble this kind of beautiful geometries. This is very specific and probably far off from real construction, and that is why we wanted to see, can we provide such beautiful surface structures in concrete? And can we do this efficiently? And indeed, you see these structures only for unique projects, like the Rolex Center in Lausanne, because they need a unique budget, which goes to this full foundation to build up all this scaffolding, and then you assemble this formwork that typically takes months or even years to fabricate, and then unfortunately it almost always turns into this after 28 days when the concrete hardens. So can we provide a lightweight system? So here, for example, fabric with a cable net. To summarize, what we're after is basically, can we replace the rigid formwork with this flexible formwork. And there is two important messages on this slide, is that actually why we have all these inefficiencies is because this word rigid, this is really brute force. Can we hold the geometry exactly where it needs to be? If we develop a flexible formwork, this is possible, but then we need to design for the deformations that we will have to expect in such formworks indeed. So what I'm trying to say is, can we use something like this to realize a concrete shell like this one? So this is a prototype that we finished in 2017, and it will be built on top of this this building where we have already the defab house, and on the other corner there will this unit be called, that is called Hilo. Might look something like this. It is a very engaged project that is now 8 years in development, but we are now on site, and this is really a project that challenges the relation between innovation and research and industry indeed. The roof was quite a statement, and indeed our client, EMPA, got a little bit nervous and at a certain point said you need to demonstrate in a one-to-one prototype that you can do what you promise. And so we started this. We did this with all the partners that would be involved, developed this kit of part that assembled a team of just 3 people to assemble the entire formwork in 1 week's time. Here I want to re-emphasize the alternative would be to basically be months and months of milling of all this material that would be wasted. So this 1 week of Meccano or Lego putting together a formwork is not that bad. Perhaps this money shot really clarifies what we're after, just with a very lightweight, by the way, 100% reusable, reconfigurable system. We realize basically the forming of this efficient shell. So here with the fabric being applied. But then, and I already made this, I hinted at this in the Armadillo Vault, you can be 100% certain that your geometry will not be there where it needs to be. So that is something, even though we have developed these beautiful optimization strategies that actually tell you exactly how to pre-stress all these different cables so that we have a non-uniform pre-camber. That means that our formwork is a little bit higher than where it needs to be, so that under the weight of the concrete it hits exactly the geometry. So we have these algorithms. We can even include hard constraints like facade lines. All of this is nice, sophisticated research. We got a paper prize for this. It was mentioned, the Tsuboy Award. But this has absolutely, unfortunately, nothing to do with reality. Because every single connection can be a little bit off. Even in Switzerland, you can be 100% certain that the boundary conditions might be off by a millimeter, or to be honest, by multiple centimeters. So this is the reality of the building site. And that means that your structure is not at all where it needs to be, your formwork. That's why we included this little axis, and we developed with our partners in scanning to actually have a system to know where your geometry is. Unfortunately, that is not the end of the story, because then you could say, okay, you told me that 100% certain the geometry will not be where it needs to be. Let's then just retighten it and put it where it needs to be. Unfortunately, if you have turnbuckles at all ends of these cables, you have about 90 trillion options. And which is the one combination of tightening and loosening that redirects it where it needs to be. This is the excitement in the NCCR digital fabrication. That is typically where this research project would stop. You would write a paper, you would say it was a good idea, but has nothing to do with reality, so too bad. But actually there's people that specialize in this. In automation control, these are basically mathematicians that know exactly what to do with your problem, because you have an equilibrium model, you have unpredictable kind of parameters, and then you need to make a decision. Typically, they apply their research to autopilot for airplanes, for example, the same idea. You have an equilibrium model, you need to make a split-second solution. Which of all the control systems will actually keep your airplane in the air? So in a way, this is a little bit of an easier or less risky kind of business indeed. This is a special moment for me because I'm selling, or I'm presenting this now as a beautiful success project from step A to B, A to Z, but believe me, we had to fight a lot of skepticism. It took us 1.5 years to even find a contractor that we had to pay at cost, so no sponsoring whatsoever. that wanted to take the risk to be involved with us. So that was challenge number 1. Then we finally found someone brave, and then the entire process, we got a lot of comments. So everyone on site was like, oh my God, these 2 youngsters there, they are making us do something that will never work. This will cost 10 times more than it needs to be. Until actually this point, because here they realized that this very funky geometry, that we reduced it to a very simple patch of 40 by 40 centimeters. And that was possible because this node that we developed became that logistical device. It basically is where all the information is brought on site. So you have the space holders for your reinforcement, you have the references for locally how thick the shell needs to be. It also becomes the connection for your shear connectors. That is also the same axis where we attach the waterproofing membranes and so on. So basically, here our partners realized, that is what they meant. That is why we did all this pre-design, this digital fabrication, and this is basically what made this project very realistic indeed. This is a project where we used carbon fiber reinforcement. That is because something that I didn't say is this 10 by 20 meter concrete shell is only 3 centimeters in thickness. And so that demanded then, of course, reinforcements that would not corrode. Also, can you imagine having to pre-bend all these reinforcements? This would be another, if you're aware of the project Stuttgart 21, this would be another Stuttgart 21 disaster in the making indeed. Then the concreting was done. So here you see how this is applied and then vibrated in place. I have to admit that there was a little bit of concrete chemistry and magic happening indeed. But that is why we have to work together with material experts to make things like this possible. So there it was standing. As you can see, this is not architectural, Swiss standard architectural concrete. This is not fair face concrete indeed, but because we did every single step with industry, and about anything that could go wrong went wrong in this project, it was actually our industry partner that signed off to the client and guaranteed that the next one would be fair face concrete, something that I would not have dared to make as a statement indeed. I also want to provoke a little bit with this quote from our engineer of record. She called our approach building information modeling on steroids. And that is because we used our open source computational framework Compass to extend indeed building information modeling approach, but more importantly to centralize all the information in this very lightweight computational model through Compass. And this allowed actually to engage a variety of partners, most of them that had absolutely no digital expertise whatsoever, but then the gray circles are these research groups. So this approach allowed us to directly transfer innovation into practice, even with partners that don't have any digital expertise indeed. And so with Compass, you can include these new algorithms, you can include the control systems, you have all the fabrication data or FE, so engineering data, all together in one model indeed. So this is now finally getting built. We are on site. There is a new challenge that we are now on top of the building. The 3 centimeters is true, but we have 2 layers of 3 centimeters. It is a novel concrete sandwich shell. And because this is a real project, we also have real constraints, like we cannot have thermal issues. So we have the thermal breaks, which is the detail that we developed here in the middle. The second one on the left it sounds maybe very specific, but this was a breakthrough innovation. This is a specific detail that allows us to have both on a structural side and both aesthetically a cold joint. And that means that basically this gigantic shell, this large surface of concrete, can be cast in very manageable stages. And so that was something that we learned the hard way, that actually you also need to have these fallback options to that it's not everything needs to happen in one go. And we can basically control the system on site. So here you see, for example, the profile that is at the glass facade. We want the glass to disappear into the concrete shell and to have visible concrete from the inside all the way to the outside. This image was a prototype to demonstrate the quality and the finish that we have, and we needed to demonstrate and guarantee to our client that we would deliver this concrete work within 5 millimeters of precision, which, if any of you know about concrete construction, typically it's a couple of centimeters, so 5 millimeters is absolutely absurd. But the reason we now found out that this was required from our system is because they didn't want to give any of the other contractors an excuse to say why they didn't deliver, because it's easy to point at the new guy and the new innovation that basically was the reason that they couldn't handle. But we are looking forward to have this beautiful aesthetics, this imprint of the fabric, a new kind of experience for architectural fair-face concrete indeed. This was the building site just before the winter break. You see that it's extremely clean, not only because it's in Switzerland, but also just because this simple kit of parts can be assembled by just 2 workers. 2 workers then together with my research team, who are now expert complex formwork installers next to doing their PhD research indeed. So this is Sandy kind of finishing a few details. So everything is prefabricated, and this thing came together much faster than what was budgeted by the project team indeed. And so here you see, maybe the finishing, the detail that I talked about, the black spine in the middle, is basically this detail to create this kind of joints. So why I labeled this under computational design is because I hope you understand that this pre-calculation, all these algorithms that allow such a lightweight, entirely reusable kind of kit of parts to be effectively used in a real project, that cannot happen just by a typical sequential process. Everything needs to be understood. I was entirely blown away when the contractor, Marti, which is a very traditional, highly respected contractor, concrete contractor in Switzerland, called me 2 weeks after the prototype to ask if we were okay that they would do a bid for a project based on this formwork system. So in a way, we seem to have convinced our local partners that this makes sense. Let's now see what we can achieve if we really also start to innovate in digital fabrication. And more specifically, we wanted to challenge ourselves. Can we do even better than the system that I just talked about? Can we go on site with something that is so lightweight that it can literally come into a backpack? And that is where we started to do research in 3D knitting of technical textiles. And this is maybe a first hint. The knit on the left is actually a non-orientable surface, like a Möbius strip. That means that it doesn't have a consistent normal. It basically falls on top of itself. This geometry came out of the knitting machine in one process. While actually, if you were to do this with a woven fabric, you would need at least 20 cutting patterns to be able to approximate this kind of knit. So in order to really fully control this system, we dove in all the way to the yarn definition and the loops and the jumps, and also activated the 2 beds in a typical flatbed knitting machine. And so the idea was, can we actually steer this machine to make these non-standard kind of geometries? The reason that we don't need cutting patterns is because the red lines that you see in there are called short rows. They're basically increases of materials locally that allow you to actually drape a non-developable surface. But it was very exciting when Mariana and Lex started to actually talk to each other. So Lex is our concrete magician, and they basically thought, what happens if we were to dump this knit into a fast-setting cement paste? And indeed, what does happen is you can then suddenly have these non-standard complex nodes that are super lightweight, and that basically could be brought on site as a very efficient stay-in-place formwork. But of course, we wanted to challenge ourselves a bit more, and we teamed up with Zayadit Architects to demonstrate this at a quite sizable scale. We called our pavilion Knit Candela. It was in Mexico City. And indeed, like Candela, we wanted to have a very expressive, thin structural shell. But Candela, as you maybe know, was able to realize his shells because he always used these high part geometries which allow to use these reusable straight line formworks. But what you also probably notice is that these formworks still use a lot of material, are very labor intensive, very complex indeed. And on top of that, the high par is not a bad structural form, but you can do much better. So can we be flexible, more flexible with respect to the shapes? And that is when this pavilion was designed indeed. So this is a quick movie of the process. The initial design sketch was done by Zayedit Architects. They also generated the pattern on the inside, but then all of this was done by my group, basically made it feasible, made it buildable. And for this, again, we used a cable falsework, so basically that carries the concrete. And then in this case, the shuttering was this automatically produced knit that could be brought on site in a very efficient way. But again, the knit serves as that logistical device that basically takes all the challenge of local erection into account. What you also saw is that this was a nice demonstration of compass. We did hundreds of iterations, and because the FE model was directly connected to the CAD geometry, we could do all of this very efficiently. So here you see Marianne and Lex just the day before they had to take their plane to Mexico City, wrap up the entire formwork that weighed only 25 kilograms and could be brought into 2 regular pieces of checked luggage indeed. So this is the scaffolding that was done by our local contractors and then or collaborators, and then we could basically, as you see here, the cables are nicely referenced by all the little channels that are elegantly included in this knit. That is something that you could not do with a woven fabric. You would need to have to do quite a lot of stitching, and this immediately becomes not realistic as a strategy. So here you see the tightening, very simple tightening, and then here the knit. Unbelievable that this 3-dimensional scarf or sock nicely fit. Some additional features to beautifully finish the shell. And then these modeling balloons, so these clown balloons, were used to inflate some pockets to basically create a nice, stable and stiff geometry. So what you see here is this specific hardening cement paste developed by our colleagues in the NCCR to make this knit stiff enough to be used as actually a stable formwork indeed. And for me, what's exciting is that we had never talked or worked or seen any of these workers, and basically we just provided this formwork, and the local craftspeople could then very cleanly finish this shell in record time indeed. Because I think I'm running out of time, I might skip through these images to maybe make a few more comments. So here you see really how transparent and lightweight this thing is. So we're talking about, well, I will come back to this. And then here you see the balloons being inserted. You also see that this is maybe not done in Switzerland because we would not be able to hang over a structure like this. But the key message is that this indeed beautifully looks like a Swiss chocolate, an indication that this must be a good idea. But what you're looking at specifically is that these inflated balloons allowed us to make these pockets. And this was necessary because we had a fiber reinforced shell, and we could not just increase the thickness because we had a weight limitation on the ground. And so what we wanted to demonstrate is what you can achieve with this knit and with nothing else. So here we achieved with this kind of formwork a structure that had stiffening ribs in 2 directions, something that would absolutely not make sense to do with a typical milled formwork, because that would be so much waste, so much cost, so much time to install this. And so here you see that we literally provided a more interesting canvas to our local colleagues that could finish then this beautiful concrete works. We took advantage also an other form of the knit. Let's expose the knit and actually provide a more tactile, a different kind of expression of a harsh concrete shell that was beautifully soft and had this other kind of experience on the inside. Why I present this project proudly, not only do we think that it has some aesthetic merits, but let me throw some numbers at you. What you're looking at is 50 square meters of concrete surface. The concrete shell weighs 5 tons, and the knit weighed only 25 kilograms. The entire formwork, so not the reusable external kind of scaffolding, but the internal formwork, so the cable net, the connectors, the knit, altogether only cost 2,500 euros. So what would that be? Less than 4,000 Australian dollars, I guess. But a killer argument is perhaps this, is that the knit took only 36 hours to be produced. And if you were to generate the same surface as a milled surface, this would have taken 750 hours, which actually translates to 3 months of non-stop milling. And then to say that the time of design, engineering, prototyping, development, installation and construction, from the first email by Zaha, the invitation, all the way to the opening exhibition took only 3.5 months. This is also an important message that with this integrated design, engineering, fabrication, construction process, we basically can significantly increase productivity and delivery on site, but we can also change the proportions between the design and development versus construction. So we really pushed everything, all the development, until we went on site. And perhaps an exciting outlook is that these machines that are used to make garment t-shirts are available all over the world, and what is cheaper and lighter than send 25 kilograms to site is just to send data to your local knitting shop and to make your formworks locally indeed. Because this is such a special event, I wanted to also show something that I have not shown to anyone, because this is entirely confidential. This is a project that will be featured in Maxi, in the museum designed by Zayedit Architects in Rome. It will open in December 2020, this year. Although with all this corona business, we might not know if this will indeed happen still this year. But for this project, we wanted to bring back an old project that was done by one of our dear collaborators, Matthias Rippmann, a senior scientist in my team that unfortunately passed away this summer. And we wanted to bring back one of his most beautiful designs, and this is what you're looking at. He called it a funicular funnel shell. It's a pure compressive vault, but then rather than coming down like these typical hobbit houses or Gaudi-like kind of curves, we wanted to actually open up the boundary condition. And so this is a purely balanced shape that is in pure compression and has one tension tie balancing it in equilibrium indeed. So this also can be done with Rhino Vault. And to clarify that these principles work, this is a very delicate 3D printed model that took a lot of effort to assemble. This just to show this is an extreme model, but what is also an important message here is something that in the architectural realm is often forgotten, is that form finding a good shape for your structure is really not the end of the travel. You still need to engineer it, and here for live load cases, as beautifully demonstrated, we might need to reinforce this structure. And that is the big innovation that we want to show in this project, is that so by the way, that's why it's knit nervy. It's reinterpreting these grid-like, concrete grid-like structures. And so we will make a concrete grid shell. So basically these very precise, crisp profiles. But on top of that, the forming system will not be an externalized tensioning frame, but will be the integrated reinforcement. So this is extremely close to making a frame of a building. Of course, we do this in an exciting shape. But so, again, what I want to say is that here we are going one step further, one step closer to reality. And so basically we will have these beautiful prismatic kind of tubes that can be poured in one go and where on top of that exactly where the reinforcement needs to be, they're integrated. So because it's not just about shaping the geometry, anyone that does research in 3D printing knows what the bottleneck is, how to reinforce these kind of new digitally fabricated structures. So we want to avoid this mess as well. Can this also be integrated in this lightweight package that we bring on site? And so yes, it can, and you will see it all hopefully in December 2020. All right, so I talked about these three aspects, but I want to now in the final project, the final piece that I wanted to show, where we bring all of this together, and we bring all of this together to address this. What you're looking at are floors. So we need a lot of floors in the world, and indeed, I didn't say something earlier. We talked about 3/4 of the weight of a building to be considered is in its structure. What I didn't say is that more than half of this weight is actually in the floors. So it is, you waste most material, and hence you pollute most by spanning space. And we already talked about this aspect. By reintroducing these structural principles of the tight arch, you can for free realize 70% of weight saving. So we thought in the same project in Hilo, can we already do this in our context? And so we designed this floor plate that only has 2 centimeters of unreinforced concrete. So this is basically a 3D version of the tight arch with an externalized tension tie indeed. We already had shown this at the Venice Biennale as well in 2016. If you thought that the armadillo vault was a point, no, that was just us shouting to get attention so that people would pay attention to the real message, which is these highly efficient floor systems. And then this is a nice demonstrator, again done by Matthias. This is a fully 3D printed floor plate, where we actually also have these discrete parts. And what's important here is that it's not just about the structural geometry. Here again, we learn from the past. For example, master builder Robert Maillard in Switzerland, who designs these 3-hinged arch bridges because these were the early days in 1929 of reinforced concrete. People didn't understand that material really well. And basically the specific geometry that you see was very carefully designed with the same tools that we now extend in 3D with RhinoVault, with graphic statics. For any loading case, he basically traced the pure compression shape that went through the 3 hinges. So he made a statically determinate system that allowed basically to understand the equilibrium of under any loading case. And what he wanted to guarantee is that the compressive lines stay always within the section, so that he would not get any surprise with this new material that was poorly understood. So we need to do the same thing, because the material, the 3D printed material that we use, so we use the voxel jet, like a large-scale sand printer, and the material properties are equivalent to what we used in Ethiopia. Peanuts in compression, and if you take a piece out, you can just break it in bending again. So this is very scary. To make our points, we did a full ACI requested loading protocol. So this is an experimental campaign until failure to demonstrate that it can take all loading cases required. If this looks too engineering or abstract to you, perhaps this makes more sense. This is almost 1,200 kilograms of ETH nerds standing on a 2-centimeter floor plate with material properties equivalent to cold dark chocolate. So this is an important message, and why I want to put this image here is because we still get quite a lot of resistance from practice that this is possible. But if you think that this is academic and crazy what we're talking about, let's go back to the oyster bar. Because what I didn't say about this shell is not only that it's unreinforced, that what you're looking at is not decoration, but one of 3 layers of unreinforced masonry. What I didn't say is that these shells are carrying the Vanderbilt Hall on top. And the Vanderbilt Hall is one of the 2 main entrances of Grand Central Station. So if you think that we are crazy, then at least 3 to 4 million New Yorkers are risking their lives going to work every single day. And this is also an important message, that bringing back these common sense principles has been quite a challenge. You have to go to extreme measures to convince that actually equilibrium, strength through geometry works, and that we should indeed reintroduce them. Because can you imagine the impact in all these high-rises that go up in all the cities and densifications all over the world, if more than 40% of the weight of the structure is into the floor plates. That means that the columns, the primary structure lighter, the foundation lighter, so everything changes. The seismic response changes, so this is a severe, severe offset indeed. And these cavities can also be activated for more optimized building system integration so that you are not just layering like Rem Koolhaas was clarifying in his Biennale, that this is a key challenge of our construction indeed. So you're not only lighter, you're not only using weaker materials, so practically no pollution, but you can also offer at least 25% more real estate because you make your floor depth lower. Don't have time to talk about the details, but Tomás Mendes, former postdoc, actually demonstrated that these structural geometries are extremely acoustically performant, and there as well, let me say the same, architecture seems to always go for the brute force way, and indeed brute force would be to add mass to acoustically dampen these shells, but actually here we demonstrate that we are using structural stiffness to activate, to be acoustically performant. And structural geometry is beautiful, that is something that I like to celebrate. But in a way, I also don't care if you replace your structure by something that is indeed 70% lighter. In the current development, only 1/6 of the embodied carbon. It's made entirely out of recycled content. What we're building in Hilo uses 100% recycled aggregate and cement with 50% recycled content. And because we separate compression and tension, all elements can just be re-shredded and are indeed 100% recyclable at the end of their lifespan. So we're building this now. This is on site because of all kinds of practical reasons. We save only 50%, so not quite 70 yet. That has something to do with fire. It's a long story. It's a non-issue. But the local engineer of record got a little bit nervous, and so we added a few centimeters to make everyone happy. And we recently successfully tested a full-scale fabrication and structural prototype. I want to come back to reiterate about this urgency. Another way to translate this one New York City every month for the next 40 years is to say that we need to double our building stock. We need to double the amount of floors in this world, and this is another reality, that we might be trying to be a good example, but it's not in our context that all this expansion, most of this expansion will happen. It will happen in Africa, it will happen in Asia indeed, and that is why I'm so proud that we are now working with the government of South Africa to providing solutions for one of their problems. What you're looking at used to be a lake that is sucked dry by all this green. This green is not good news. These are non-indigenous plants and bushes and trees. A key issue for the entire African continent, that these introduced plants and trees in colonial times are not matched to their climatic kind of reason. They suck entire aquifers dry. They make indigenous plants die and so on. And the government has developed this fully certified material that actually ships cuts all of these bio-waste and has developed a concrete-like material with 70% biomass, where all the aggregate and sand is replaced by this biomass. It's in South Africa fully certified, fireproof, termite-proof, and even gunshot-proof, something that is important for safe housing solutions in Cape Town, for example. So what we are challenging, what we have now a commission, we will build this in September, a first prototype where we show that we again can reduce this, because what do we offer? Good structural form allows us to take almost all the cement out, and as you also noticed, is we take practically all the reinforcement steel out, so that makes it cheaper and more sustainable at the same time, and that is a beautiful outlook. It's not the first time that we did this. In Addis Ababa, I've done a project entirely with local people together with Dirk Hebel. We trained local vocational training people to provide an 80 square meter housing solution that entirely finished cost only 3,500 euros. So that is less than 40 Australian dollars per square meter. So that is the finished product here. So I'm looking forward to now, after 10 years of intense research, to use all our computational and digital fabrication expertise to provide systems that are dummy-proof and that can activate local labor and give new construction opportunities in South Africa. So what we talked about, or what I talked about, is that structural geometry allows us to use less material. Funicular form, which means vaulted geometries, allows us to use better material. And through smart implementation of digital fabrication, we are providing solutions to realize these beautiful forms with no waste or very minimized waste. Because of all this urgency, and I already said this, we really believe that we all need to work together. That is why we have developed for the last 5 years this open source framework, because we want other people to be able to do what we do. We need to start learning from each other and building upon each other. And last, I want to finish with an overview of my team. This was my team in March 2019. That is almost a year. That is a year old. But I wanted to put these people on the slide because most of the projects that I've shown were done by them. And that is something that I need to acknowledge, that I'm thankful to have an absolutely spectacular team, passionate team that helps me hopefully change the world a little bit to provide these necessary, desperately necessary, disruptive solutions to hopefully do much better as an industry. I'm sorry that I went a little bit over time. That is maybe because of the peculiar context. But please go to our website, because unlike what publishers want us to do, we share everything on our website. So you can download any paper, you can use all our tools if you want to, and so on. So thank you for your attention, and I'm very happy to take any question.